Hello, my name is Kalen Baker, and my mentor is Dr. Ping He, and today we'll be discussing the evaluation of americium's molecular dynamics parapotential for alpha voltaic modeling. So first I'll discuss what an alpha voltaic power supply is, and then we'll move into the rest of it. So if you're going to capture nuclear energy, there are three ways. One is with a nuclear reactor, where you split atoms using neutrons, and the recoil from the fission fragments generates a substantial amount of heat that can be used to generate steam and turn turbines. The second is kind of what NASA uses and to power their deep spacecraft. You get about a 30-pound block of plutonium, and it glows under the heat of its own decay, and you can put thermocouples inside of it, and those thermocouples generate voltage that can be used to power the spacecraft. The third, which is the one I'm interested in, is this direct capture method, which comes in the form of these alpha voltaic and beta voltaic devices. And so what happens is, as it decays, the decay particle gets discharged inside your semiconductor, and that generates an electrical pulse that can be used to power your device. And so these devices are quite small. They're about the size of a dime and can be built onto whatever you're concerned with. One of the other more important things is that they don't require any maintenance like a nuclear reactor would. And so you can use it to power things that don't see a whole lot of human hands, like radio tracking tags, anything north of the Arctic Circle. In some of the more unusual cases, they were used to power pacemakers at one point because they are very long lived and don't require intervention. The problem is that as these devices run, the radioactive decay actually damages the semiconductor converter at the end of its discharge path, and so it loses efficiency as time progresses. So in order to correct this, we need to make new designs and new materials. Much like a solar cell has an optimal wavelength of absorption, there are optimum materials that are better absorbing the radiation than others, and so these need to be checked. But first, we need to check compatibility of the material before we actually start building them. The same thing with designs. Typically, when you build one of these devices, the radioisotope is built as a thin foil and it gets laid over the top of the device. Well, the first problem is that it heavily damages one side of the converter. The second problem is that half that face is exposed and it's not being used to convert into useful energy. So there's a lot of wasted potential there. The problem is that in order to separate radioisotopes, it's about $10,000 to $20,000 an ounce to separate an isotope. And so this is very cost prohibitive, and to discover that you've built a bunch of prototypes that don't work. But we're also talking about radioisotopes. While alpha emitters are fairly safe as long as they stay outside your body, there's definitely some risk associated with handling them for an extended period of time, because the longer you handle them, the risk that you contaminate yourself goes up. And so to simulate working with these materials, it's best done with molecular dynamics, where we can see the idiosyncrasies of them bonding to their semiconductor. We can see if the new designs are going to work out before we physically have to build a device. So the isotope I'm interested in is americium-241. But the problem is that in order to drive one of these molecular dynamic simulations, you need a parapotential, which specifies the force interaction between any of the molecules in the simulation, and it doesn't exist here. So we have to start working with a potential that's very easy to build. In this case, it comes in the form of a Litter-Jones potential, and all it needs is these two constants to be specified, and then from there we can move forward. That third item listed in the bottom is given by the simulation. It's not something we really control, so we're only really concerned about supplying those two variables to the simulation. So we look over here at the right-hand side, and this is typically what one would use for a metal material if it existed. Its form is a little bit more complicated, but you see there's only these three variables. The problem here is that electron density is actually quite complicated to calculate, and so in the end, making an embedded atom method is really, really difficult. And so we went with the Litter-Jones. So we'll talk about the materials I'm interested in. I chose titanium, uranium, and americium. So titanium is some that I've worked with before. Its properties are well known and it's easily described, and so it's just a good place to make use of some previous data and a good starting point. Well, americium sits far out at the end of the periodic table, so there's not a lot of information. So I find the next closest element, which is uranium. And the two elements in between, neptunium and plutonium, are much like americium. There's not a lot of useful information that exists for it. So uranium's just going to have to do. So we look at these pictures here in the bottom, and it's just an example of the crystalline structure. We see HCP here, double HCP over here, and this hexagonal close packed, and double hexagonal close packed. Then we get orthorhombic in the uranium. So what these are describing is the crystalline structure. And so in order to generate a pair potential, what we do is we make an assumption. You make an assumption it's either body-centered cubic or face-centered cubic. And what this does is make the crystalline structure symmetric, and it simplifies the mathematics involved in generating a pair potential, but it causes some problems I'll discuss here in a moment. So my simulations, had to split it in two. The first simulation was interested in the melting point and some other physical properties. And reason I had to split in two is I was tracking the potential energy, which is how I'm going to measure my melting point. And the thermostat and the baryostat needed to regulate the conditions inside the simulation, affect the energy of the system. It kind of sort of bumps it back into band. And so this would affect my reading for melting point. But the same control system I use for the melting point simulation affects my diffusion simulation, so I ultimately had to split them in two. And this little asterisk right here by thermal conductivity. So when I tried to calculate it, there was some more physical phenomena that I was unaware of at the time, but once I started calculating it, what I have is some phonon phenomena that I didn't know to account for. And because I have infinite perfect crystal because of the wrapped boundaries inside my simulation, what happens is there's nothing to stop the propagation of these phonons inside the structure, which is what I'm using to kind of sort of calculate my thermal conductivity. If I was going to get a thermal conductivity reading from a regular material, it's all polycrystalline. There's individual grains and there's discontinuities that affect the way these phonons propagate. And so the thermal conductivity reading is much lower. And so without a way to correct for it, the thermal conductivity reading had to be disregarded because it's just so much higher than any actual usable result that you would get from a real experiment. So my computer here, this prototype is a proof of concept I built 2 years ago. And then with help from the Office of Undergraduate Research, I built this final assembly. It's 15 Raspberry Pis. Each one is functionally its own computer. And what I've done is I've linked them all together to act as a single computer. And so what I can do is split my simulation into parts using the software, and each part gets sent to one of the cards. It processes results and sends it back to the primary card. And then from there, the primary card reassembles the result. And what it allows me to do is take much less time to calculate very complicated scenarios. That being said, took me 27 days of real time for the computer to run all of my simulations. And that's just the results here. Currently, I'm working on lining out some discrepancies that I had, and I'm about at 31 days worth of runtime. So there's a lot of time been invested in just watching the computer run to perform these simulations. So we'll start with my set of results. We get titanium here, and because the other two elements took priority, the melting simulation didn't get a chance to be run here. It's currently in progress. So if we look at my picture down here, they're both exactly the same, but what I've done here on the right is zoomed in on the melting point. And what we see is that the embedded atom method here, this red line, begins to make a sharp curve up. And what this actually is melting point behavior. What happens is as you get closer to the melting point, rather than jump from latticite to latticite, as it gets more molten, the atoms are now free to move around wherever freely. And so that's what we're seeing here is them beginning to freely move. And so what we've captured is the melting point through the diffusion simulation. Even though that wasn't the point of this simulation, it shows that we get the melting point quite well. But if we look at the Lennard-Jones potential, we see roughly a flat line, and it's not really particularly helpful in this particular instance. So then we move on to my uranium simulation where I was able to complete all of my runs. So we have this enclosed one here. This is my melting simulation. And so as I started to drive the simulation well past the melting point, I needed to evaluate something because at this point I realized it should have melted. So with a discussion with one of the other professors, melting happens in regular things at a different stage than perfect things. Regular things are imperfect, and so the melting starts at these imperfect positions, and it actually causes melting to happen much, much lower. Perfect things, it goes to a much, much higher temperature, which is what we're seeing here in this enclosed. So to generate a defect and initiate melting, what I did is I exposed the face on my simulation, and now we're going to see this sharp turn up here at the melting simulation, which is what I expect to see. When things melt, they release a large amount of energy, typically called the latent heat of fusion. And so that's what we're catching the end of here. Now, if we look at my diffusion simulation, once again, we have kind of a similar set of results like the titanium simulation. The embedded atom method begins to show a curve up where it begins to melt, and the Lennard-Jones potential is roughly flat. But we see here that my Lennard-Jones potential is very close to this beta uranium crystalline structure in terms of diffusion data. And so we clearly see that there are probably some low temperature applications for this uranium potential. But if we look at the thermal expansion value that I calculated here, we see there's quite a large discrepancy, and this leads back to the crystalline structure difference that I was talking about before. And so I would like to go back and potentially build a pair potential that actually uses the real crystalline structure, though the mathematics behind it get way more complicated. I think the value here would be more useful in that particular case. So then we move to americium, and my only potential that I have is my Lennard-Jones, and it doesn't work well. Rather than be that straight line we see in all the other ones, that same linear behavior, it immediately goes non-linear, and it's molten probably before it even gets past the end of the beta phase. Um, and this isn't what we expected to see. And so, not to be disheartened by that, I continued to perform the melting simulation. And once I got past the minimization step and began to try to run the experiment in earnest, what the temperature did is go to about 4,000 degrees and then stay there. And nothing I could do could bring the temperature back down. And so, what we learned here is that the Lennard-Jones simulation in this particular instance is unstable and will need some modification. So some of the issues I ran into is, well, we know that the Lennard-Jones potential is not going to work well for its high temperature applications. The low temperature applications, there is some promise. But the other thing I had issues with was finding modern information. This is the best that the Cold War could provide me, and I suspect or the rest of the papers I'm looking for are much in a similar state, either classified because of the Cold War or just recently declassified. But the problem here is that these all sit in older databases and they have to go and manually be combed out by hand for a lot of it. And so it makes finding any sort of modern information or any information at all very difficult. But not to be discouraged, the Lennard-Jones potential, one of the great things about it is that it's easily modifiable. That 12.6 that we saw on it is just one of the formulations. It's just one of that generates decent results. 9.6 is another form, but those exponents can be changed to better reflect a more metallic system. And so with that, we could probably make some corrections to my simulation. That being said, the constants can also be changed, so there's a lot of room to work with the Lennard-Jones potential. But while I was running the rest of the simulations, I looked into a different type of simulation. It's called a first principles calculation. Rather than use the laws of Newton's laws of physics and motion, it uses quantum mechanical principles to solve for material properties. And so in this particular instance, when I tried to look for a pseudo-potential for americium-241, we have much the same problem that we had when we were doing it for a normal molecular dynamics simulation, and that there's no pseudo-potential that exists for americium-241. But if we had one, I know for sure that we could use it to build an EAM potential. There's software that makes it capable to do so. And from there, we could build a working potential because we see that the EAM potential behaves very well for what I'm attempting to do. And with that, I'd like to thank the Office of Undergraduate Research, my mentor and Dr. Ream, and Dr. Fan for assisting me in this project.